Hello everyone. What I would like to do in this pre-lecture is talk about electron configurations and orbital diagrams. Okay? Now, we've talked about orbitals. We've talked about that any one orbital can hold 2 electrons. We also talked about what orbitals were in each energy level or shell of an atom. So let's review just a little bit here. So let's start with the first energy level, the first shell. Okay, we talked about that there's only the 1s orbital in the first energy level. That's it. And then as we go up in each energy level, we add a new type of orbital. So in the second energy level, we have the 2s. Every energy level has an s orbital. And then we also have the 2p subshell. I'm going to draw 3 dashes here to represent that there are 3 different p orbitals. Okay, there's the 2px, the 2py, and the 2pz. All right, and we've talked about that as well. All right, so there's actually 4 orbitals in the second energy level, and each can hold 2 electrons. Total of 8 electrons could be held in the second shell or energy level. Now we move up to n equal to 3. Again, we have an s orbital. We call it the 3s orbital. Remember, this is increasing energy, and it's also increasing distance of the electron from the nucleus. All right, so the 3s orbital is larger than the 2s, which is larger than the 1s, and so on. All right, we also have 3p orbitals, 3 3p orbitals, okay? And now we're into the third shell, the third energy level. We add a new type of orbital, and those are the 3d. Again, the 3 is just the n value. And so we have s, p, and d orbitals. Anytime we have d orbitals, there are going to be 5 of them. You don't need to know the names. You know, there's 3dxy, 3dxe, 3dyz, and so on. But know that there are 5 of them. All right? 5 d orbitals in a d subshell. And then, let's do one more. N equal to 4. We have the 4s. I'm going to have to make these a little bit smaller, I think. The 4p. Again, 3 p orbitals in a p subshell, the 4d orbitals, and then a new type of orbital, and those are going to be the f. And there will be 7 f orbitals in an f subshell. All right, so you can see as we go further and further from the nucleus, there's just more space. There's a lot more space. All right, and so we need more orbitals, more regions of space for the electrons to exist. So in the 4th energy level, remember the number of orbitals is n squared. So in the 4th energy level, 4 squared. If you add those all up, you're going to count 16 orbitals in n equal to 4. Okay, 32 electrons total. All right. Now, let me scroll down here a little bit. I have some slides from our notes. You might think, so this is kind of what we just did. Now, the one thing I didn't show in my diagram is that the delta E between 1 and 2 is the largest of any of these. And then as we go higher up, the energy levels or shells get closer and closer together in energy. You know, so this is the largest delta here. This delta E is going to be smaller. And this delta E is going to be even smaller, and so on. They get closer and closer together. Now, you might think when we start to fill the orbitals, we're going to fill from lowest energy, which is the 1s. Okay, we're going to start with the most stable place for the electrons, and then we're going to work our way up. So you would think probably 1s, 2s, then 2p, 3s, 3p, 3d, and so on. Unfortunately, it's not quite that simple. Because for a number of reasons. And one is, as we get closer, as we go further and further away from the nucleus, these energy levels are just closer together. Okay? And there's another reason. And let's go to the next slide, and we can look at the actual ordering. Okay? And so, initially it looks pretty good. We're going to start with the 1s, then the 2s, then the 2p, then the 3s, then the 3p, 4s, before the 3d. Now, why the heck is that? Why does that happen? Well, first of all, the 4s and 3d are pretty close in energy to begin with. As I mentioned already, as we get further and further from the nucleus, the energy of the orbitals get closer and closer together. The difference is the 4s orbital, it's right over here, on average, an electron in a 4s orbital is further from the nucleus. So you would think that that's higher energy, and indeed it would be, but an s electron, so an electron in an s orbital, is what's termed more penetrating. Okay, it can get closer to the nucleus. Okay, so a 4s electron can get closer to the nucleus than a 3d, for example. All right, so even though a 3d electron, on average, is closer to the nucleus, there are times when the 4s electron can get even closer than the 3d. All right, so it turns out because of the greater penetrating nature, the ability to get closer to the nucleus of an s electron compared to a d, the 4s electron is slightly lower in energy than the 3d. Okay? So this adds a little confusion. It'd be nice if we just went 1s, 2s, 2p, 3s, 3p, 4s, or 3p, 3d, 4s, 4p, and so on, just like the order we started with here. Okay? It'd be nice if we just did that same simple order, but we don't. But the cool thing is, you don't have to memorize the order. Guess why? Because of the periodic table. Isn't that exciting? The periodic table is laid out just as the orbitals fill. Okay, it's laid out just as the orbitals fill. That shouldn't surprise you because, again, we group things in columns based on similar properties. And you might then expect then they should have similar electron configurations, as we're going to find out. So we start at the top. And I'm going to write atomic numbers in here because the atomic number is the number of protons. But then if it's a neutral atom, which is what we're going to look at initially, that's also the number of electrons. So 3, 4, 5, 6, 7, 8, 9, 10, and so on. So these are the atomic numbers again. And 18 for argon. So let's just stop there for now. So we're going to fill electrons in that order. Now the nice thing is, as you can see labeled here, the first two columns of the table is where the s orbital fills. Remember, anytime we have an s orbital, there's only one of them. So just 2 electrons. Remember, 2 electrons in any one orbital. Over on this side of the table, this is where the p orbitals fill. Okay, how many p orbitals are in a p subshell? How many? 3. Okay, 3 orbitals in a p subshell. 2 electrons per orbital. How many electrons in a p subshell? 6. Let's count across. 1, 2, 3, 4, 5, 6. How about that? Exciting. Okay? The middle block of the table where the transition metals are, the orbitals that are filling there are the Ds. How many orbitals are in a D subshell? You guys know this. 5. Very good. All right. 5 orbitals. Total of 2 electrons per orbital max. That's 10 electrons. Let's go across. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Amazing. Okay? And then, down at what are called the lanthanides and actinides, and as a group, they're called rare earth elements, lanthanides and actinides. That's where the f orbitals fill. How many orbitals in an f subshell? 7. 14 electrons max, and if you count across 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Get the idea. Okay, so the periodic table is just laid out for you how the orbitals fill. Now, we start here, 1. So this is where the 1s fills. Okay, so electrons 1 and 2. And then we come to the 2s. Okay, that can hold 2 electrons. Then we come over here, just coming across, this is where the 2p subshell fills. Again, 6 electrons total. Then the 3s. Then the 3p going across here. All right? Then we have the 4s. Now, what they're trying to show you here, 4s, as we noted above, the 4s is slightly lower in energy than the 3d. So it's going to fill before the 3d. So even though we're in the fourth row, 4s, after the 4s comes the 3d, then we're back to the 4p, and so on. Now, I typically have you know down to 6s, because what happens here is this would then be the 5d, and if you look at a normal periodic table, it doesn't show you in this one. We actually jump down at this point to here, which is the 4. Oops, sorry, I hit something with my palm of my hand. 4f. Okay, and the reason why we don't spend too much time with the f orbitals is that by then the energy levels are really close together. And since they're so close together, there's many exceptions to what we would list as the normal order of filling orbitals. Lots of exceptions. And we're going to talk about some exceptions that are up in this region of the table. Let's say right there, actually, and right here. We'll do that in class. But there are some exceptions you need to know, but there are so many exceptions to the normal order of filling in the f orbitals that we typically won't deal with those when writing electron configurations. All right, let's at this point, now that we have kind of a mess here as I drew on my periodic table, if you really struggle with using a periodic table, and you'll see this in your book, there is a little chart you can make up where you just write 1s, 2s, 3s, 4s all the way down. Then next to the 2s, you write 2p, 3p, 4p, and so on coming down. And then the 3d comes in, you write the d. The f comes in, you write the f. And then you just draw arrows across. And this is the correct order of filling. 1s, 2s, 2p, 3s, 3p, 4s, then 3d, 4p, 5s, and so on. I don't recommend that. I think you really need, if you really want to know how to do this, you need to know how to look at a periodic table and just write them out. All right. So for the most of the remainder of this pre-lecture, I'm just going to play an animation that goes through some examples of electron configurations, and then it's also going to talk about something called an orbital diagram, which is related to an electron configuration. Right? And then I might do one more example just to refresh at the end. But let's go to an animation, and hopefully this will record the audio okay.
An electron configuration of an atom shows how the electrons are distributed among the various atomic orbitals. The periodic table is arranged to show which subshells are filled as we progress across and down the periodic table. Oxygen has an atomic number of 8, meaning that the atom has 8 protons and 8 electrons. To write the ground state electron configuration, we start with the 1s orbital and continue to place electrons in orbitals of increasing energy until we reach 8 electrons. Recall that any one orbital can hold at most 2 electrons. Starting with the 1s orbital, which can hold 2 electrons, we write 1s2. Next, the 2s orbital can hold 2 electrons. We write 2s2. We have placed 4 electrons, meaning there are still 4 electrons to place. There are 3 2p orbitals, which can hold a total of 6 electrons. We place the remaining 4 electrons in the 2p orbitals and write 2p4. The ground state electron configuration for an oxygen atom is 1s2, 2s2, 2p4. Double check that you have placed 8 electrons. 2 plus 2 plus 4 equals 8. We use a box to represent each orbital. We place electrons based on the Pauli exclusion principle and Hund's rule. 2 electrons are placed in the 1s orbital with opposite spin. 2 electrons are placed in the 2s orbital with opposite spin. We place 1 electron in each of the 2p orbitals with the same spin. The 4th 2p electron is paired up in one of the 2p orbitals with opposite spin. This is the ground state orbital diagram for an oxygen atom.
All right, right, so hopefully my audio is back on. So make sure you note a couple of things here. The orbital diagram just gives you more information than the electron configuration. It gives you the spin of the electron, and when we pair up, we're going to pair up with opposite spin. Remember we talked about that a spinning charged particle generates a magnetic field, and so by pairing them up with opposite spin, the magnetic fields cancel out, and that's a lower energy configuration. The other thing to note is we will try to keep the electrons as far apart as possible if we can before we pair them up, because electrons are all negatively charged, so that if you have the same charge, negative in this case, they're going to repel each other. So since we have three orbitals in the p subshell, the 2px, the 2py, and the 2pz in this case, we're going to put one electron in the 2px, one in the 2py, one in the 2pz. That takes care of 3. We are going to have to pair up the fourth one. Okay? All right, so that's oxygen. Electron configuration, still written below 1s2, 2s2, 2p4, that's 8. And then the orbital diagram gives us more information. Let's look at another example here.
For an oxygen atom, calcium has an atomic number of 20, meaning that the atom has 20 protons and 20 electrons. To write the ground state electron configuration, we start with the 1s orbital, which can hold 2 electrons. We write 1s2. Next, the 2s orbital can hold 2 electrons. We write 2s2. The 3 2p orbitals can hold 6 electrons. We write 2p6. Thus far, we have placed 10 electrons. The 3s orbital can hold 2 electrons. We write 3s2. The 3 3p orbitals can hold 6 electrons. We write 3p6. The final 2 electrons are placed in the 4s orbital. We write 4s2. The ground state electron configuration of a calcium atom is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Double check that you have placed 20 electrons. We can simplify this electron configuration by using the noble gas core configuration of the noble gas element that most nearly precedes the element being considered. In this case, the noble gas would be argon. The argon core configuration accounts for 18 electrons. We add 4s2 to account for the final 2 electrons. We start with the shorthand representation.
All right, so in most cases, I will let you use the shorthand configuration because as we go further down in the periodic table, that's going to, these electron configurations can get quite long, as you can see even with this one. So we start with the noble gas in the row preceding, and then that makes your life easy because that takes care of 18. We only have 2 electrons. Now again, note we're in the 1, 2, 3, 4th row. This is where the s orbital fills, so it's 4s2 in this case. Not too hard. Now let's do the orbital diagram. I think we're going to do the shorthand configuration here as well.
For the electron configuration of calcium. We add a box to represent the 4s orbital. The last 2 electrons are placed in the 4s orbital with opposite spin. This is the ground state orbital diagram for a calcium atom. Remember that the notation argon in square brackets represents 18 electrons.
Okay, so that makes your life a lot easier for an orbital diagram too, because if you had to write it out for everything, you'd have a 1s orbital, 2s orbital, 2p orbitals, 3s, 3p, and so on. But know how to do both. Typically, as we get further down in the table, I'll let you use the shorthand configuration. And let's do one more here.
Nickel has an atomic number of 28, meaning that the atom has 28 protons and 28 electrons. Let's start with the ground state electron configuration with the noble gas core preceding nickel. We start with the argon core, which accounts for 18 electrons. We have 10 electrons left to place. We move to the 4s orbital, which can hold 2 electrons. We write 4s2. There are 5 3d orbitals, which can hold 10 electrons. We have 8 electrons to place, so we write 3d8. The ground state electron configuration of a nickel atom is argon, 4s2, 3d8. Double check that you have placed 28 electrons. Remember, the argon core represents 18 electrons.
Okay, so one thing to note here, if you look at the 3D area, count across. So the 3D again is this middle block of the table. So count across 1, 2, 3, 4, 5, 6, 7, 8. There's your 3D8. You'll notice that we could hold 2 more electrons in the D, but we've already gotten to nickel with 8. This would be 9, 10 out to zinc, so look at a periodic table. So zinc would actually have 10 electrons in the 3D. All right, and let's do the orbital diagram here.
We use a box to represent each orbital. We place 2 electrons in the 4s orbital with opposite spin. We place 1 electron in each of the 3d orbitals with the same spin. This accounts for 5 of the d electrons.
Okay, so again note, when you have a subshell, you're going to try to keep the electrons as far apart as possible until you have to pair them up. Okay, until you have to pair them up. So 5 electrons, 1 electron in each of the 3D. Now we're going to have to start pairing them up.
The remaining 3 electrons are paired up in 3 of the d orbitals with opposite spin. This is the ground state orbital diagram of nickel.
Okay, there you go. Electron configurations, orbital diagrams. Again, the orbital diagram is just giving you more information about the spin of the electron and how many electrons you have in a particular, how they're spaced out in a particular subshell. Okay. Let's do one more example just to wrap this up. Okay, so let me come back to here, and let's try iodine. Okay, so look at a periodic table, and you'll see that iodine has an atomic number of 53. So as a neutral atom, it will have 53 electrons. All right, and I hope I'm recording audio here. I've been switching back and forth trying to mute things, so I'm not picking up too much stuff. I hope this is working. Let me go back here real quick. Check, check. Okay, I'm getting some audio. That's good. Okay, we're at 22 minutes, so I need to wrap this up. So 53 electrons. Now, if we try to do all 53 of these, right, we'd have to start with a 1s, 2s, 2p, 3s, 3p, 4s, or 3d, I got confused. But anyway, you get the idea. But what we're going to do is we're going to go to the noble gas in the row preceding iodine. And if you look, you'll find that that is krypton. And that takes care of the first 36 electrons. So that saves us a lot of time, okay, because now we only have 17 electrons left to place. So look at the periodic table. Come down below krypton. You'll see we're in the 5th row of the periodic table. And I'm going to scroll back up here just to show you on my chart here. So we're at this, so krypton is here, okay, that's 36 electrons. Now we're going to start in the 5th row. So we're going to fill the 5s. Remember the d's are 1 behind, then the 4d, and then we're going to be into the 5, here's iodine here, we're going to be into the 5p. So 5s, 4d, 5p. All right, so 5s, that's just one orbital. How many electrons can it hold? 2. All right, the d subshell. How many orbitals are there in the d subshell? 5. Each can hold 2 electrons, total of 10. 5s2, 4d, 10. I'm going to scroll back up. We're then going to be in the 5p. And how many electrons do we need to put in the 5p? 1, 2, 3, 4, 5. Okay, we don't need to fill the 6th one. We're not going all the way across the noble gas there, which is xenon. We're stopping here at iodine, 5 electrons. So sorry about jumping around, but 5p5. And if you count now, we place 30, krypton represents 36. 2 more would be 38. 10 more would be 48. 5 more, 53. There you go. Now for the orbital diagram, all we have to do, we're going to start with krypton again. We're going to put a line or a box, either way, but typically a box. 2 electrons in the 5s. All right, and typically we use half arrowheads, spin up, spin down. We're going to have to draw 4 boxes. I got my 4D. 5 boxes for the 4D orbitals, can hold 10 electrons. Now, these are going to be filled and everything paired up, but if we were normally filling these, we'd go 1, 2, 3, 4, 5 until we have to pair up. And they will all have the same spin. We typically start with spin up. So we'll make them all spin up, and then we start pairing up spin down. Okay, so there's our 4d10. How many orbitals in a p subshell? 3. 5p subshell, 1. It's 5p5. 1, 2, 3. Unpaired, we do have to pair up 2 of those. There you go. Electron configurations, orbital diagrams. I think they're pretty straightforward. Not too bad. Okay? Learn to use the periodic table. It will really help you whether you're doing these in the homework, whether you're doing these on a quiz. It's really helpful to be able to just look at a periodic table and write them out. Okay, that's enough for this pre-lecture. Take care. See you in class very soon.